Guess it's expanded. 10. All right, so yeah, so why don't I just go through this thing? I kept adding things to this, So I just added a paper just now, This thing, homework 8 starts like here, and there's all these papers with it. So did you bring a computer with you? Did you download the Igor thing yet?
Oh,
You downloaded it? Yes?
Yes.
Okay, good. Then we'll use your computer. Can you log into Zoom then? Like to get this, so like will you, because I can't use mine because mine uses the same Zoom account as this thing's using. So when I do that, it'll kick us off this thing. But we can use your computer. Anyway, it's better to use yours so we can see how to do it. I just wanted you guys to see kind of how that Igor thing works. And kind of just so you get familiar with it a little bit. And it's not anywhere near like what it can do, but so we can try that. Let's see now. I have to go back to Zoom. Did it say recording like we could hear it? It did? Okay, good. All right, so we're okay.
Professor, the camera is not focused in a right position.
Oh, that is weird, huh? All right. Let's see. Handheld mic. Yeah. It does it. Maybe I'm wondering why it does that. Dock camera, wireless VGA. All right, I'm looking at it. Oh, camera up here. I think it's just that it has to spin around. It's pointing to the back of the room, right? Oh, wait, it says recall preset 1. Oh, wait. Oh, shoot. All right, wait. I just hold on. All right, recall preset 1.
Recall preset 1.
That's not good. Do it again.
Yes. Not do that. Recall preset 1.
That did it?
Just begin to dock preset.
Okay, you should be doing this. I see. Okay. All right. The display I have, okay, is delayed from that. So what I see is it doesn't work. Oh, wait. That's wrong. Anyway, that's kind of okay. All right. Hopefully that's all right. Is that all right?
Yeah.
All right. I'm going to leave it. All right. You want me to zoom more?
Yeah, those
all right. See, my display here doesn't show that anything happened. So, all right. So, yeah, this paper. So let's see. Okay, so homework 8, and then this paper. Mora. So it's a Japanese group, and they're working at this. I put in a link for the place where they did this. So it's just what he said, this JPEG thing. JPEG, yeah. So it's this is the machine. Just this shows like, all right, so they have an accelerator that blasts into a piece of metal, and then they have all these instruments that come off that thing, right? So that it'll be like, this is like the source, and then everything comes out off it. So oh, I see. Proton beam is here. So this is probably a SANS machine. This one goes out, super HRPD, and then see, this is one of these backscatter. See how it's a big arc? So a person is probably this, like people lie down, this would be like 6 people across. So it's pretty big. No, it's like a kind of fairly large scale thing. And then he showed pictures of it, right? But there was no context, like there's no person there. Where's JPEG? And then,
So that's J.
yeah, but this is the beamline they use, BLO. See, it's this huge detector. This is like a wall. So a person's height is like half of this thing. So that's like 4 people high. And these are all detectors, all these helium detectors he was talking about all around this thing. So it's kind of an interesting thing to see, you know, and you can see there's a lot of optics in it. So it's just what he was saying. It's like a bouncing off the crystals and then whatever. So you get some pictures of how the thing works. Anyway, so they're doing this problem, right? That's been around a long time. So the idea that you have when you make a network, right? And then is it better to have, so you can make anionic chains, and then so you can get a monodispersed network. It's possible to do that. Or you can have like a polydispersed network. You have short chains and long chains mixed, right? And like the question is like, which one's better? So if you like normally, if you're gonna make a tire, you take a rubber and you just put a crosslinker sulfur into it. So you get like a explosion of chain lengths in it. There's a huge polydispersity in it, right? So, but if you want to, you can cross-link in solution at a low density, and you can get just the end links, and you can just get this perfect structure, which looks like it would be better than a cartoon, right? So it turns out like polydispersity is always better. Anything that's polydispersed is always going to be better, you know. So basically, in this paper they're arguing the opposite of that, you know. So they're saying, well, they make these things, they're both made in kind of a model thing. So he has a short chain that he introduces. They're both kind of cross-linked in dilute conditions. And he says the one that's hetero with the short and long, it breaks first. So it breaks there. And then the one that's homo, it has a little, it stretches further. It's extension at failure is like 7 times. So they don't, in this kind of thing, they don't plot strain, stress and strain. They plot stress and extension ratio. So 1 would be a strain of 0. And then this would be a strain of 6. Like 1 minus that gives a strain. So anyway, so he makes a gel. He makes these gels, or hydrogels. So it's PEO PEG, so polyethylene oxide, polyethylene glycol, and then it's got these N-link functionalities. So it's the same carbon-carbon oxygen chains, and then it swells in water. So you can get a swollen network. And then he puts them in this weird rig. It's got cadmium up here, absorbs neutrons, and then he's got these strips, so you can put it under strain. So he can take that thing and stretch it and then stick it in the beam, right? And then from that, he gets this decay pattern. So if you have no, so basically there's a spike, that would be like the main beam at 0 energy transfer. So that means it's an elastic beam. That's like elastic scattering. Then there's this broad decay that kind of follows a Lorentzian, like 1/1 plus energy squared times some constant would be like this Lorentzian kind of peak thing, right? But so, or you can fit that. So typically you fit it with this like an exponential decay in time. So it has frequency, then this is a time decay. Before it transforms time, it gets frequency. So it's like you're going to get the inverse units when you Fourier transform. You have real space and it transforms into Q, or you can have time and it transforms into frequency, right? And it's what it's doing is taking a sine waves into it and saying each sine wave has a certain frequency, and what's the amplitude of each sine wave, and summing those up, and you're going to plot the amplitudes versus frequency instead of the signal you had in time, which is just this featureless decay thing. And he's saying that the things that are given rise to that frequency response. So frequency is proportional to energy. It's like h nu. So that's like energy. And then there's going to be a series of exponential decays, but they're not normal exponential decays. They're this kind of stretched exponential. So it's got this power. And the power is, if it's 1, then it's just a normal exponential decay. It's going to be a series of those that are summed together. So the weird, I mean, one thing that's weird is that if you take a series of exponential decays, there's no imaginary number in this, right? And then you say it's going to be a sum of these exponential decays. Well, that's the definition of a Laplace transform, not a Fourier transform. So it's kind of weird to say this is a Fourier transform. It's really a Laplace transform because there's no imaginary number in this. Like if it was I times exponential or exponential I t over tau, right? Then that would exponential minus I of two numbers to give unitless. That's going to be a series of sine waves, right? You add together, but this is going to be a series of just exponential decays. There's no I in this. So when you add up exponential decays, that's a Laplace transform, right? And when you so it isn't exactly really a Fourier transform here, I guess, as far as except the Q part is, but the time part kind of isn't, you know. So they're coupled. So that's a convolution. The X circle thing's a convolution. So the Q and the time are coupled. So you could say it's a Fourier transform, I guess, as that part has, the other part has kind of a imaginary to it. Anyway, this is how he did it. So from that, from the fits of these things, he gets an average relaxation time for each condition that he has. So each of these curves, you get one of these curves, like Nicholas showed, you get one of those curves for every Q. So they're going off in Q, you have all these decays. So at each Q or each size scale that you probe, the material relaxes differently. So if you go to really small sizes, the material doesn't know it's in a network. So it just diffuses with Brownian motion, right? So you see the signature time goes with size. So the mean squared distance, so the squared distance goes with time. Mean squared distance goes with time times the diffusion coefficient. So the slope of that would be the diffusion coefficient. So this is Brownian motion. If you see time and size and power 2, that's Brownian motion, right? So that's good. That's like the normal world. Then you get to larger and larger sizes. So you reach some cutoff at 0.5 inverse angstrom, and then it's different. It's not Brownian motion anymore. So the options are Brownian motion or ballistic motion. Those are your two usual options. So ballistic means distance you travel is proportional to time. So you'd see a slope of -1. It was ballistic motion. Like you put proteins into a charged field in a gel, the motion you'll see is ballistic. They fly across to get to the other side because they're charged molecules, right? So you'd expect to see, like, maybe at small scales, you'd see diffusion, then you see a transition to 1. That would be like guided motion, say ballistic motion. If it's bigger than 2, that means that that's faster than diffuses. That's super diffusive motion. It's faster. And if it's steeper, it's subdiffuses, even though it's a bigger slope. It means it's moving slower. It means that the Brownian motion is being hindered by something. You don't know what, but something's hindering it, right? So he said, so it goes to 3. So it kind of makes sense if you have a network and small scale, it's diffusive. And then at larger scale, maybe when you reach the network size, then it's going to be hindered, right? So you go to this 3. So these are just unstrained, and he has the solution. So the chain's just in solution, and then the chain's in a gel, the solution in gel, and they kind of just behave the same way, except that. And he's fit to get the tau, he's fitting it with a stretched exponential, this beta power thing. So the beta isn't 1. If the beta is 1, it's just normal exponential decay. If beta is some number smaller than 1, then something else, like the shape isn't right. It's not exactly exponential decay. So in fact, the broader this gets, the broader the decay function gets, the lower the beta. Okay, so if you are broader the response is. So if you take glass transition, this beta comes out of glass transition. It's called the fragility. So if you run a DSC, so there's no enthalpy at a glass transition. There's just a change in the slope of the heat versus time, whatever. So the heat flow versus temperature. Right, so you're going through the glass transition, and the slope of the heat flow versus temperature is the heat capacity. So because when you get to the glass, things can't move as much, they have less capacity to store heat. So they have a lower heat capacity. And when they move more in the liquid, they have more capacity to store heat. So you have a higher heat capacity. So you have a higher slope and then a lower slope. And the transition between those two in the DSC curve is a glass transition. So that could be a sharp transition, or it could be a broad transition. Either way, it's a change in slope, so it's not something you can exactly put your finger on. Like you do a derivative and plot the derivative of heat capacity, and you can see like a sharp step function. that would be beta's 1. That's a perfect exponential decay. If you see, like, instead of a sharp step function, so you go on heat capacity, so the derivative of the DSC curve is flat, and then it doesn't go jump and then go to the other number, but it's got like a sigmoidal thing, like a broad thing, then beta's 0.8, right? So that when it's 1, that's called a fragile glass, right? And when it's less than 1, it's a non-fragile glass. So this becomes like a whole area where people like will go down the rabbit hole, deep down the rabbit hole, right? You can spend a lot of time thinking about fragility of things, and then you can spend your whole life talking about fragility of things, and it doesn't seem to really mean much, you know. It's like, but basically there's whole meetings on fragility of glasses and different kinds of transitions where they have this exponential decay, but fits with this beta thing, right? So he's down that rabbit hole too. So he's got his beta number, and if it goes to 1, it's just a normal fragile transition, like a sharp transition. If it goes less than 1, it's a broadening out of the transition in temperature, say, for glass transition. But so anyway, that's what he's got. He's got that as a function of Q. So when he gets to this hindered tau part, where he has subdiffusive motion, right, where the things can't move diffusively anymore because they're stuck. Then he gets beta, he broadens out the transition too. So that kind of makes sense. And at the same point, at 0.5. So he's got kind of Brownian motion, and it's fragile, right? And so it's a sharp transition. Then he goes to a broad transition, and it's subdiffusive. Both of those kind of are consistent with each other. So it's nice that he sees that. So he does that, and then he sticks a thing in his machine. So those are all done with no strain. Then he sticks it in the machine and stretches it. He goes to like lambda 1, lambda 2, lambda 3. So 3 times. So think this is a gel. It's like Jello, right? And he's pulling it 3 times the length. A lot of strain. 300 strain of 300, right? 300% strain. Like 3 times you pull it out. It's not metal. It's like, you know, it's like a really stretching the thing. And then he sits there, and this measurement takes 2.5 or 3 hours. Yeah, so he sits with the Jello in a clamp, stretched it 3 times its length, and he waits 3 hours, you know. This is starting to give you some kind of idea, like this isn't really working out. Like the thing will relax, right? It's the stress relaxation. It's gonna just, it's gooey stretching. I mean, eventually there'll be no stress on it at all, right? So it'll just be a mess, kind of. So anyway, that's what he does. So he has different strains, 1, 2, 3, right? One's from this plot, and 2, 3 are the 2 stretches he does. So when lambda is 1, that strain is 0. There's 1 minus that gives a strain. So it's actually a strain of 100% and 200%. And those are the curves. He's shifted them, I think, up and down so you can see them. And then this is the result of that for the homogel. So you see the diffusive regime when he stretches it. So when he doesn't stretch it, it goes to subdiffusive. When he stretches it, it's still diffusive all the way through. Like it's as if he doesn't have a constraint anymore. So that's kind of weird. I mean, that's right off is pretty weird. The time gets faster. So, right. So it's a faster dynamics. The things are moving. So when he stretches it, they move faster and they diffuse. It's as if they don't see the network anymore. Right. So something weird is going on there. He kind of explains that. He still gets this kind of behavior where he sees less fragility or more kind of broadening of the transition when he gets to below 0.5. So that part doesn't change, but this thing changes pretty significantly. I mean, if you think about it, it's a log scale, so there's a big change in the relaxation time, and also it doesn't change mode here. So he gives an explanation for that. All right, I think it's something, I don't know, I didn't really remember his explanation. You can read it, it's short, it's like a paragraph, but he talks about why that would happen. This doesn't seem that logical to me. Then he does the same thing for his other guy, and he finds out nothing changes. Nothing at all changes. He stretches it 200% strain, and he gets exactly the same tau and exactly the same beta. So the only change he sees is when it's homo. When he gets the hetero, There's no change at all. And he says, that's because, and this is where he had an idea when he went in, when he first made this experiment of what was going to happen. And then lo and behold, he finds it out, right? This is the answer. So because all the strain goes into the little things and the big things aren't changed at all. That's stress concentration at the small chains. And this is his evidence for it. And it seems to be pretty strong evidence. All right, so that's kind of the point of the paper. I think that there's a lot of problems with this paper, though. Like, first off, stress relaxation is a huge problem. Second of all, the reactions aren't perfect, right? So normally if you're gonna do modeled gels, so then you would like take the gel, make it, and then de-swell it, and then swell it in the solvent again, like water. So you can get and wash it kind of to get rid of the chains that didn't react. Right. And then you'd measure the modulus of it so you can get the cross-link density. So then you could tell, like, you could project like what the cross-link density should be in your mind and what it is actually. And that means there's a lot of dangling ends in it, like change. So his cartoon doesn't show any dangling ends. There's no like 3 functionality junctions here, which there's going to be some. You don't know how many. So to really study this stuff realistically, like you'd have to. And if you have a 3 junction, that means you're going to have extended lengths, not just 2 modes. You'd have like at least 3 modes. Like some would be 2 things long instead of 1 thing long. You know, so it's complicated. It's not so simple the way he talks about it. Not anywhere close to as simple as he talks about it. So, yet he gets pretty clean results that verify exactly what he wanted them to verify. So if you reviewed this paper, you would kind of reject it. I think that's what I think. I don't think this should have been published the way it was published, but nonetheless, so he's got some interesting things. So one thing is this stress strain plot isn't really the way. So you can see if you want to get the modulus, there's no place where this goes straight, right? That's because in a normal, if you put a piece of metal into an instron and pull it, right? The reason that it stretches is because the bonds, the atoms are separating as you pull it, right? So it's not an incompressible fluid, it increases in volume, right? So there's a volumetric strain that's put on the material as you pull it. And when that gets too high, it breaks. So it breaks brittly, right? This kind of material isn't like that at all. So lambda is a strain. They have lambda 1, lambda 2, lambda 3. Lambda 1, lambda 2, lambda 3 times each other equals 1, and it's fixed. It's incompressible. It's like a liquid. So liquid is incompressible. So this thing's incompressible. So when you pull on it, you don't get that kind of bond stretching, and even shows kind of what you get. Like you get some kind of rearrangement, right? In other words, it rearranges into something else. It can pull in from the sides. So you can see he's got lambda 1, lambda 2 are equal. When you have that situation, you don't get a linear part to this tensile curve. So you can't really do a tensile measurement on that kind of material. So this business was known for a long time. So you have like Flory 470, 474, right? So just get this. So let me just zip over to this thing. So this is Flory's first. This is kind of like the first book on polymers. So he's got a chapter on what he calls rubber elasticity, where he goes through, and that's kind of like the Bible. This book's more or less a Bible of polymers, you know, in a sense. It's from like 1960 something. 470. So he's talking about, so this is the same thing, like tension extension ratio. So that's a lambda. And then he's got this, let's see. So he calculates the entropy of a chain, and he figures out like what the stress strain relationship should be, and should depend on this modulus, on this cross-link density of a rubber, which is this guy also has. And then let's see. Anyway, 474, he gets to the 474 here. So he's got like this equation with C1 and C2 and then stress. So stress, then alpha is the strain, our lambda, right? So if you divide, and the C1 is C1's the modulus, right? So it's not a linear dependence between stress and strain. That's the first thing. It's going to be this curve dependence, and this function, which comes right out of the free energy calculation for the change. So he's got lambda 1, lambda 2, lambda 3 equals 1, and he's incompressible, right? So you get this equation for an incompressible fluid. And then this C1 is going to be the modulus. And the modulus, you remember, for rubber is like 3 kT over the molecular weight between crosslinks, and which is NL squared, right? So basically, the molecular weight between crosslinks, if you have a fixed density of chains, that ends up being the number of crosslinks per volume. The molecular weight between crosslinks is 1 over the number of crosslinks per volume. If you have more crosslinks, you have shorter chains, right? So okay, so the modulus here is going to be like the rubber elasticity modulus, and then this number. So you're going to have to take the stress divided by this alpha minus 1 over alpha squared versus 1 over lambda, because this term would be this thing times 1 over lambda. In other words, 1 over alpha, that thing goes to 1, 1 over alpha, that goes to 1 over alpha cubed. So you divide by this, and they have C2, 2 times C1, which is a modulus, plus 2 times C2 times 1 over lambda. So you plot tau over this thing versus 1 over lambda. That's called a Mooney-Rivlin plot. And then the intercept, so if this has a slope, the intercept is the modulus. Instead of doing a linear fit to get the slope as a modulus, the modulus is actually the intercept here, where you go to 0 strain, right? So, or 0, 1 over lambda. So I guess whatever that is. So anyway, so that's the plot that you need to make, is this Mooney-Rivlin plot. So and then there's other modifications to that. So this is the modulus, and then what is C2? Like, so what is C2? C2 is this, okay? So these are invariants of a tensor, of the strain tensor. So there's 3 invariants because it's a 3D tensor. It's like it's change in X with X, change in X with Y, change in X with Z. So it's like a 3D, so it's like 3 invariants you get from that 3D matrix, right? There's 9 terms in it, and then you get 3 invariants. So the first one is this alpha, alpha, alpha. The last one is the incompressibility. So that last one is just 1. The third invariant is 1. If it's in an incompressible fluid, it's that thing. And the second invariant is this weird thing, 1 over alpha squared, some of the inverses of the thing. So anyway, so these are invariant with respect to rotation of the coordinate system, right? So that's the idea. Invariant means like you can rotate the coordinate system, these things will be the same. If you change X, Y, and Z, you'll get the same number out of these, right? You can see, like, if I swap X, Y, Z, the sum of the squares is going to be the same. Or any angular dependence, it'll be exactly the same. That's why it's called invariant, right? So mechanics, this is continuum mechanics. So it's complicated and pretty messy and kind of useless, you know, because mostly you're going to be doing a tensile or a shear measurement. In a shear measurement, the modulus doesn't have this problem because you aren't putting any stress on the volume in a shear measurement. So if you want to measure the modulus of a polymer, you probably want to do it in shear if you can, because you don't have to mess around with this stuff, right? So anyway, so we need to do this Mooney-Rivlin plot to figure out what this is. Oh, and what is C2? By arbitrarily choosing appropriate value C2, much better fit to experimental as possible through the use of first term alone. So the first term alone is just that you can get that, he gets that in this book on 470 directly from the thermodynamics of a rubber chain, of a chain being stretched, right? Incompressible chain being stretched. The second term is kind of added in. It's the second invariant. So he doesn't say what it is. That's the point. He gives a star here. I don't know where the star goes. Blackwell has shown very good agreement, has attained wide range of vulcanized, blah, 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 using the constant C1 varies with the modulus. So basically C2 is this black box thing, okay? If you look, I mean, that's what I see that Flory says about C2. If you look, there's some notes here from a guy, Hervé Morin, from Virginia Polytech. He's retired now, but he goes through rubber elasticity and some kind of simple slides. This is the Flory thing. So if you do it from free energy, you end up with that equation, which is just the modulus and that other term. And then if you want to include the Mooney-Rivlin, you need that C2. Finally, he says that C2, he says that Flory says that C2 has to do with the looseness of the network somewhere here. Here's this, anyway, so the looseness of the network, C2 over C1 measures the looseness of the network. And he claims that Flory says that, but Flory in the book at least doesn't exactly say that. So Flory published a bunch of papers on this too. So anyway, C2, if a network, so his network in our paper, I mean, you could look at it this way, the network isn't loose at all. So there's just no kind of dangling ends and things in this thing. So basically, I guess that means it's not loose, so C2 should be 0. That's my argument anyway. So it turns out like C2 equals 0. So anyway, so you have do you have Igor downloaded on your computer, and are you in the Zoom thing?
Yeah.
So let's go through your thing. I have to share. I have to stop share. And then I have to allow share. So let's go right there. So you got so can you share your screen in Zoom? See if that's gonna work. All right, that's good. Sit down if you want. The bank's gonna get messed up. All right, so it's an Amore or something, Amora. Yeah, and then go to figure 3. Make it bigger, up there, so right there, right there. Then make it bigger. Yeah, much as big as you can make it. Right, that's good. Then copy just that thing.
Sounds very good.
Yeah, just get, no, not a screenshot, just get that thing, just a plot. Or get the screenshot if you can. The bigger you make it, the better. That's good. Yeah, that's great. All right, now take that to a file. So like you need a file with like either a PDF or a PNG or TIFF or something. Is it already a file? No, it's a snippet to yes, save. Or open with some graphic thing or something like PowerPoint like this. You have to save a graphic file. Hit the PNG thing. Okay. You know where you saved it? I sent home my page. Right. Oh, yeah, that's good. That's good. Okay. Then you go to Igor. Then over something. Display new regular stress versus versus R and what is that? So I think like digitizing what is great. All right, so we got that. So anyway, that's how you, so you can see like this is a simple thing to kind of mess around with ego, but there's a lot more you can do. You can write programs. Anyway, so let's go back to so you got to release your thing. Stop sharing. You have to stop share. I don't think I can do it for you. Maybe I can, but I don't exactly know how. So anyway, if you do that, then you can go back to the Mooney-Rivlin stuff. So there's a paper in here that tells you what to do with the C1. So it's called am I sharing?
You're sharing.
I'm not sharing. Okay, thanks. Okay, so it's called homework 8, paper on Mooney-Rivlin. So this is like a simple idiot's guide to Mooney-Rivlin, use of Mooney-Rivlin, right? By some guys in Thailand from a long time ago. But you can see there's a lambda minus lambda 1/2. That's a plot we made. This number is 0. We got C1. And from C1, you can get the crosslink to how many crosslinks per volume. C1 over RT gives you moles of crosslinks per volume. If you figure out the units of RT, C1 in this case is in kilopascal. And then R can be in units of Pascal per centimeter cubed or something or other. Mole per centimeter cubed in Pascal. They'll cancel out, and Kelvin's in it. And then you'll find out that this N physical for our gel is about 10 times smaller than what he gets in this. Like in this, he gets that. See, he's got a C2 because he's got imperfect networks, and we have kind of perfect networks. Our number is going to be 0.4 in this unit. It's mole per centimeter cubed. So we're about 10 times less crosslink than he is for a rubber. He's got a rubber. He's got a swollen rubber, right? So anyway, so you can get that from his plot, and you can kind of, if you want, you don't have to, but basically you can compare it with what crosslink density he claims, and I think you'll find out that they aren't the same number, and also, so anyway, there's a few things you can tell from the Mooney-Rivlin. That's the right way to plot a soft matter. Like if you put in skin or liver or something into an instrument, that's the plot you need if you're going to do a tensile test. Better is to do a shear test, because then you don't have to worry about this mess. Right, so anyway, that's kind of the picture of this paper, I think. It's a short paper, okay, so shouldn't be a big deal. I also put up a bunch of other things. So talks about what that beta means. That's not a question in the homework, but in case you want to know what a stretched exponential is, and this Weibull distribution is tied to the stretched exponential. So you can kind of glance at that if you want. He cites, for this power 3, he cites this DeGen's paper from 1960 something, which is incomprehensible, but you can look at it. And then Nichols' talk is in here. The paper Nichols was talking about is there. And then this is a paper from 2021 doing simulations, kind of the same topic, like what happens when I put in short chains and long chains. But he does it he crosslinks in a simulation, and he changes the density of the chain. So if the chains are dilute, he gets N linking. And if the chains are concentrated, he gets a messed up network. So he plots. So the modulus changes a lot, and the one that's more messed up has a better modulus, opposite of what this paper decides. Okay, so, and this is the normal way to think about it, that the more messed up your network, the better the properties, because it's got this polydispersity. So he might want to glance at that. That's also not in the homework. So this thing is just use the Igor and do what I just did, right? And figure out if you can get the modulus of the thing. And then this is time of flight and backscatter. Nichols talked about that a little bit. Some of these you can put into ChatGPT and it gives a pretty good answer, but sometimes it's wrong. I mean, most of the time there's a big flaw. I mean, so I can tell right off if you use ChatGPT, but you can check the ChatGPT answers and then kind of see if your answer more or less coincides and figure out where it screws up, because it does screw up on these answers. I put them in to see what it would say. So, I mean, the advantage of time of flight, it does a really good answer for this. It says like it's better Q resolution, better energy resolution. It gives all the reasons why time of flight is better for QENS, quasi-elastic neutron. So ChatGPT answer is good, but reword it if you take it from that, This one, stretched exponential, fragility, the curves, then this is, so the fact is that he gets, the curves are completely different, right? Like this curve and like this curve, they're absolutely different, right? If you look at the values he gets for tau and beta, which are the only two parameters that are being fit, they're exactly the same between this thing with the sharp to the left and the other thing with the broad, right? And then part of it is he uses a different function to fit it. So he throws in this other term that he calls a delta, this A term, A del, which is the spike in the middle. But there's no spike in the middle, in this thing. So anyway, this thing, the A1 is 100 times smaller than A2, which means this thing's kind of insignificant. You can see like that little thing is nothing compared to the whole. So it isn't this that changes the shape. And the tau and the beta are the same. So how does he get it to fit that and to fit this with the same parameters? That to me seems to be like a pretty weird thing. There's probably an answer for that, but the numbers are the same. See, these are the same numbers. So the blue curve is the zero strain. That's one of, so somehow this thing isn't, it's the same scale. Like everything's the same, It's like what's going on? This is a different Q. Like it's a different Q here than there. So anyway, something weird is going on that he gets the same taus, Like this is 0.8 and that's 0.35. I think the first one's 0.35. He says in the caption, 0.35, and these are 0.8, they say right in the graph. So anyway, there's something weird about that the taus are the same, tau and betas are exactly the same across I think that's kind of questionable. Then the hindered subdiffusive behavior. And then he says that's because of the Zim model. So the Zim model means that you have fully entrained solvent in the chains, right? So you can get kind of slower motion because of that, I guess. I don't know. Anyway, the Jen's paper is specifically about that, but it's too complicated to read. So maybe just piece together what the Zim, and this is the thing ChatGPT can answer too, but it gives a wrong answer. So just look at D and see what you can get out of it, basically. It's like, what is a Zim model, which is just that the chain takes a solvent with it everywhere it goes. So the chain is a ball and the diameter is the end-to-end distance. That's all there is to the Zim model, right? So basically, how would that give you subdiffusive motion in a network? So you can think like at high Q, small sizes, the chains can move around and you don't see the solvent. So when you get to larger sizes, somehow it's a clump. The Zim model's kind of saying it's a clump, and then you would get subdiffusive because it's all constrained or something. DeGennes mathematically derives that in this paper, but it's almost indecipherable. Maybe you could figure it out. It's hard to tell. Anyway, so D is harder to answer, but don't use the chat. You can look at the ChatGPT answer for this, but basically it's wrong. It's not a right answer. You'll notice like what it does every time it like says, what is the Zim model? What is subdiffusive motion? It defines, this is how you should answer questions, like what is this to do with that? So you say, this is this, that is that. And then you pick the parts. So what ChatGPT picks the parts that match up, and then it gives a paragraph like, that's what they have to do with each other. It's perfectly logical. Like that's the way you should answer questions. It's doing the right thing. It's just sometimes it messes up. Like it doesn't really know. It doesn't have any idea what the Zim model really is. So it's just parroting things. Okay, the last thing, he gives an explanation for all the plots of tau and beta, and paraphrase, like it's 3 paragraphs, I think. Just paraphrase that. Then say you had chains that were, say he mixes the short and long and it phase separates. So you get the short all cross-link somewhere and the long all somewhere else. So he really has homogeneous and then some maybe domains in it. That's possible, because different kinds of chains don't mix usually. Or they didn't all cross-link, or the stress relaxation while he's doing the measurement. So how do those things impact what he says? And I think you should be able to find out that you can totally undermine his argument if you use any one of these things. And if you use all of them, you can kind of say that what he's saying is completely nutty. So the last question I'm trying to ask you to like reject this paper, like say how he messed up, like even just from an experimental point of view, if you pull on Jello and hold it, it's going to relax. It isn't going to stay stretched, so he hasn't even considered that. All we'd have to do is do that in kind of an instron and watch the stress decay and see how much time he had before he didn't bother to do that. Like you can do that in any lab, right? So, or you can just put a weight and watch how the length changes with time, right? That's also kind of stress relaxation. So you wouldn't even need an instron. Anyway, so E is kind of critique him. Say what he says and then critique it. This is what you do when you review a paper. You have to restate what they say, then say that's wrong, that's wrong, that's wrong, that's wrong. Right. So E is to get you to kind of do that, briefly in this thing. It's a short paper. So hopefully that's okay. It gives you rubber elasticity and it gives you like the other stuff. There's a lot to it, but email me if you got problems with it, I guess. Hopefully it's okay. And it shows you to use the Igor, like at least it introduces you to trying to use it, so you can kind of see what it can do. It's good for just making nice graphs, like you can make really professional graphs with it. It does 3D graphs, it does any kind of graph. You can make movies with it, like movies of 3D objects moving around and stuff. And then you can program with it. You can use it to run machines. It's got an interface to go to machines. It's a pretty good program, and it's pretty broad scope. It's got a word processor built into it. So you could program a thing. If you could put artificial intelligence, you could program it to write a paper. You could. I mean, basically, if you can link to the internet, so you could link to ChatGPT, then spit it. You could do it. You could write a program to write papers in Igor. Just ChatGPT every piece of it, and then say like, put your data and have it analyze it. It's possible to do a lot with it. We've run machines with it and then do the analysis and the same thing. So it's pretty easy. And you can put it all into pull down menus or into panels. So it's got pretty good user friendliness. But it doesn't. The problem with it doesn't write standalone programs. You have to use Igor to run its programs, and it's $800 a year or something. So the price is high. But I have educational things. So yeah,
Like license.
yeah. So it's costly to, but the educational I get for almost nothing. So
Do you know username?
no. But don't send it to Nigeria. Because I know the guy, I talked to the guy on the phone the other day, and he's like, maybe within a select group or something. It's only good for a year. So, but basically, if they start getting like a lot of stuff from Nigeria, the guy's going to come down on me pretty hard. Because he already did. I was talking to him about something else, and he's like, oh, is this really educational? And it's like, yeah, it's educational. So anyway, just be careful what you do. Don't have it show up on a chat group somewhere, so anyway. They do a good job. I mean, it's a good program, they do a pretty good job on it. So I mean, they deserve the money, I guess. It's just like too much money,